The simplest solution to the problem of maintaining the correct air-fuel ratio in response to throttle settings at all operating altitudes is the float chamber carburetor. The float chamber carburetor employs two basic principles. They are the U-tube principle and the Venturi principle. The U-tube principle states that if a tube is bent into the shape of a U and then filled with liquid, the level in either leg will be the same, provided that the pressure acting on each end of the tube is the same. If a pressure difference is created across the U-tube, it will cause the liquid to flow. In the float chamber carburetor, one leg of the U-tube is opened out to form a small tank, and a constant level is maintained by a float and valve mechanism regulating the flow of fuel from a fuel pump or pumps, delivering a supply from the main aircraft tanks. Bernoulli's theorem states that the total energy in a moving fluid is constant. The fluid possesses energy because of its pressure, temperature, and velocity. If one of these changes, one or both of the others must also change to maintain the same overall energy. As the air passes through the restriction of the Venturi, its velocity increases, causing a drop in pressure and temperature. The pressure drop at the throat of the Venturi is proportional to the mass airflow, and this is used to make fuel flow from the float chamber by placing one leg of the U-tube in the Venturi. Engine suction provides a flow of air from the air intake through the Venturi in the carburetor to the induction manifold. This air speeds up as it passes through the Venturi, and a drop in pressure occurs at this point. Air intake or atmospheric air pressure acts on the fuel in the float chamber, which is connected to a fuel discharge tube located in the throat of the Venturi. The difference in pressure between the float chamber and the throat of the Venturi provides the force necessary to discharge fuel into the airstream. As airflow through the Venturi increases, so the pressure drop increases, and a higher pressure differential acts on the fuel to increase its flow in proportion to the airflow. In this simple carburetor, the airflow to the engine is controlled by a throttle valve, and the fuel flow is controlled by a metering jet. Although this simple carburetor contains all the components necessary to provide a suitable air-fuel mixture over a limited range, modifications will be required if it's to give anything more than this basic service. To maintain the correct rate of discharge of fuel through the main jet, the pressure in the float chamber and the air intake must be equal. Equalized pressure conditions can only be obtained by connecting the float chamber directly to the air intake by a duct, which is called the pressure balance duct. As engine speed and airflow through the Venturi increase, the proportion of fuel to air rises as a result of the different flow characteristics of the two fluids. This causes the mixture to become richer as the engine RPM increases. In some ways, this may be looked upon as serendipitous. After all, at high engine power, we need a rich mixture. However, this is a bit hit and miss, and it doesn't allow any accuracy in setting the mixture. To overcome this effect, some carburetors are fitted with a diffuser, as shown here. As engine speed is progressively increased above idling, the fuel level in the diffuser well drops, and progressively uncovers more air holes. These holes allow more air into the discharge tube, and by reducing the pressure differential, prevent enrichment of the air-fuel mixture. The process of drawing both air and fuel through the discharge tube also has the effect of vaporizing the fuel more readily, particularly at low engine speeds, which assists the complete combustion of the fuel in the cylinders. At low engine speeds, the volume of air passing into the engine is so small that the depression in the venturi may be insufficient to draw fuel through the main jet. A considerable depression exists above the throttle valve, and this is utilized to effect a second source of fuel supply for slow-running conditions. A slow-running fuel passage with its own jet leads from the float chamber to an outlet at the lip of the throttle valve, as shown here. The strong depression at this point gives the necessary pressure difference to create a fuel flow. The size of the slow-running jet is such that it will provide the rich mixture required for slow-running conditions. An air bleed, opening into the choke tube below the throttle valve, assists atomization. The purpose of the transverse passage drilled through the throttle valve is to evenly distribute the mixture over the area of the induction manifold. As the throttle is opened, the depression at the lip of the throttle valve decreases, and the depression in the venturi increases to the point where the main jet starts to deliver sufficient fuel, and the flow through the slow-running system slows down. Carburetors must be carefully tuned in order to obtain a smooth, progressive changeover between the slow-running and the main system to prevent flat spots. A flat spot is a period of poor response to throttle opening caused by a temporary weak mixture. It normally makes itself felt as a hesitation during engine acceleration. A cut-off valve is usually incorporated in the slow-running passage and is used when stopping the engine. When the cut-off is operated, the valve moves over to block the passage to the slow-running delivery. The mixture being delivered to the engine becomes progressively weaker until it will not support combustion and the engine stops. The idle cutoff prevents any possibility of the engine continuing to run erratically due to pre-ignition, and also prevents fuel condensing in the cylinders, which would tend to wash the oil from the cylinder walls, causing lack of lubrication when the engine was next started. The cutoff may be a separate control, or it may be incorporated in the mixture control lever. As we stated earlier, as altitude increases, the weight of air drawn into the cylinder decreases because the air density decreases. For a given intake velocity, the pressure drop in the venturi will decrease as ambient density decreases. However, the fuel flow due to the pressure drop doesn't decrease by the same amount, and so the mixture will become richer. This progressive richness with increased altitude is unacceptable for economic operation. With a needle-type mixture control, such as shown here, a cockpit lever is connected to a needle valve in the float chamber. Movement of the cockpit lever moves the needle in the jet, and varies fuel flow through the main jet. The position of the needle therefore controls the mixture strength, and in the fully in position will block fuel flow to the main jet completely, thus providing a means of stopping the engine. These jets are the smallest orifices in the whole fuel system. To prevent any blockage of the jets by dirt or debris, a fuel strainer can be fitted just before them in the fuel line. The air bleed mixture control shown here operates by controlling the air pressure in the float chamber, thus varying the pressure differential acting on the fuel. A small air bleed between the float chamber and the venturi tends to reduce air pressure in the float chamber, and a valve connected to a cockpit lever controls the flow of air into the float chamber. When this valve is fully open, as shown here, the air pressure is greatest, and the mixture is fully rich. As the valve is closed, the air pressure decreases, thus reducing the flow of fuel and weakening the mixture. In the carburetor shown here, the valve also includes a pipe connection to the engine side of the throttle valve. When this pipe is connected to the float chamber, by moving the cockpit control to the idle cut-off position, float chamber air pressure is reduced, and fuel ceases to flow, thus stopping the engine. If the throttle valve is opened quickly, airflow responds almost immediately, and a larger volume of air flows through the carburetor. The fuel metering system, however, responds less quickly to the changing conditions, and a temporary weakening of the mixture will occur, known as a flat spot, or at worst, causing a weak cut, before fuel flow again matches airflow. This condition is overcome by fitting an accelerator pump, which is linked directly to the throttle, and forces fuel into the venturi whenever the throttle is opened, as shown here. In some pumps, a controlled bleed past the pump piston allows the throttle to be opened slowly without passing fuel to the engine. In other pumps, an additional delayed action plunger is incorporated to supply an additional quantity of fuel to the engine for a few seconds after throttle movement has ceased.